Communication channels do not care about your data. Copper wires, fiber optics, and wireless frequencies are noisy, unpredictable environments. Pushing hundreds of unorganized pieces of information into a network at once causes them to collide, scramble, and drop entirely before reaching the other side. To guarantee that a message survives this physical gauntlet intact, engineers have to impose strict, unbending discipline on the transmission process. The most extreme version of that discipline begins with a single unit of data. Let's call it packet 0. To navigate the channel safely, the sender follows an absolute rule. Dispatch this one packet, stop all operations, and wait. By stripping communication down to a single moving item, the sender and receiver eliminate collisions entirely. The large amber section is the payload. Above sits the steel blue header with routing instructions. A sequence number is embedded to track the packet. Finally, a calculated checksum is attached. If electrical noise damages data in transit, this math exposes the error. A packet is a highly engineered, self-describing, mathematically verifiable envelope built to survive an unpredictable environment. The moment the sender pushes packet 0 into the physical channel, it freezes all other operations. It will not process or prepare another frame. This space-time diagram maps that physical movement. As time progresses downward, the amber line tracks the packet crossing the physical distance from the sender to the receiver. When the packet arrives, the receiver intake process begins. It calculates its own checksum based on the data received. If the new calculation matches the packet's embedded checksum, the receiver confirms the payload is intact. The receiver then issues an acknowledgement, or ACK. This signal travels back across the channel to the sender. The arrival of this ACK is the single event that can unfreeze the sender and permit the next packet to launch. This rigid send, wait, acknowledge loop establishes a reliable baseline for communication, but it assumes the channel will behave perfectly. Network hardware drops data all the time. If a packet vanishes mid-transit, the receiver never sees it, and the sender is left waiting for an ACK that will never come. On this diagram, we see the sender's safeguard, a strict countdown timer. If the timer depletes to 0 before an ACK arrives, the sender assumes the packet was lost and immediately transmits an identical copy from its backup buffer. The exact same safeguard triggers if the packet arrives successfully, but the returning ACK is destroyed on the way back. When the ACK is lost, the sender's timer expires and it retransmits. As a result, the receiver is handed a perfect copy of a packet it has already processed. To resolve this, stop and wait uses a single-bit sequence number, toggling between 0 and 1. When the receiver sees a sequence number it just accepted, it recognizes the duplicate, discards the packet, and reissues the missing ACK. Sequence numbers in this protocol do not count the total volume of data. They exist strictly to distinguish a new piece of information from an automated retransmission. Total loss is only one hazard. Electrical noise can flip individual bits of data without destroying the physical frame. The receiver catches this subtle corruption when the math and the checksum fails to match. This split-screen timeline compares the two ways a system can handle that corrupted frame. The receiver can silently discard the bad data and force the sender to eventually time out, or it can issue a negative acknowledgement, a NAC, prompting the sender to immediately resend the data. These rules form a finite state machine. Both the sender and receiver cycle rigidly through predefined operational states: idle, transmitting, and waiting. Protocol engineers build these formal state machines to ensure that every single physical network failure, from total loss to subtle corruption, has a pre-programmed, mathematically unambiguous response. The cost of this absolute reliability is the extreme opportunity cost of stopping to wait. This space-time diagram tracks the two distinct time variables of transmission. The short vertical bar is TT, the physical time required to push the bits onto the wire. The long diagonal path is TP, the propagation delay to cross the physical distance. This efficiency formula demonstrates the protocol's structural flaw. Because the sender waits for the round-trip propagation delay, 2 times TP, the vast majority of the cycle is entirely idle. If you apply this dynamic to a high-bandwidth satellite link, where the transmission rate is extremely fast, but the physical distance to orbit is massive, the math breaks down. On modern, long-distance networks, guaranteeing correctness one packet at a time requires wasting over 99% of the channel's physical capacity. To fix this massive inefficiency, engineers developed sliding window protocols. Sliding windows decouple the act of sending from the act of waiting. By allowing multiple packets to be in flight simultaneously, the sender can keep the transmission pipe continuously full while acknowledgements flow back asynchronously. Stop and wait is functionally identical to these advanced systems. It is simply a sliding window protocol with a window size strictly capped at 1. The exact mechanisms established here, the countdown timers, the mathematical checksums, the acknowledgements, and the sequence numbers, were adopted directly into TCP, the foundational protocol operating the modern Internet. While restricting data transmission to a single packet is mathematically too slow for the modern web, the uncompromising rules of stop and wait form the indestructible DNA of all reliable global communication.